just now. So the idea behind today is that you always build a new function off of previous functions. You always build a new operation. What I'm calling an operation, you guys should be thinking of as a function. You've all learned a function where you take two numbers, you plug them in, and you get a single number out. This is the addition function. Addition, you did define as an operation you did before. I don't know if you realize this because you did addition so long ago, but it was actually defined in terms of a previous operation. Addition was repeated. What? It became a way to repeat something that you know how to do.
Counting on your fingers?
Yeah, it was repeated counting. And when you count by ones, typically. So it's repeated counting by ones. You then learn subtraction as the opposite of addition before you moved on to the next major operation several grades later. Remember when you first learned multiplication, you learned it as repeated
addition.
It was repeated addition. Instead of counting by adding, you started to learn how to simplify and skip over ahead. But the more we start to increase the scale of these operations, the greater they become difficult to imagine. We have this, also known as this, something to the somethingth power. But this is really just repeated. And I guess what makes this kind of sequence a little bit tricky is that in the case of the first two operations, the order that you did the numbers in didn't matter. Both addition and multiplication have what we call the commutative property, meaning they can be done in either order. 2 plus 7 is the same as 7 plus 2. 2 times 7 is the same as 7 times 2. But 2 to the 7th power is 128, whereas 7 to the 2nd power is 49. These are not the same thing. Which means that this operation, x to the 2nd power, we kind of call that raising, or specifically that's called squaring. But when I do x to the 7th, I don't call it seventhing. I don't have a special name for it. We just call it raising to the 7th. And if I input lots of numbers for both of these, I'm going to get the same basic shape for both of them. The same basic shape. You know what squaring looks like. It looks like this. Believe it or not, the 7th powering looks something like this. The right side of that curve looks the same. The left side dips down because the 7th of a negative is a negative. So it flops down to the other side. But this is not what we're focusing on today. We're focusing on this operation. This operation has a different name. It's not raising to the 2nd power. The name we're going to use is we call this exponentiating. It's tricky because it has a lot of syllables. But it's not just exponentiating. It's exponentiating with base 2. And that 2 could be other numbers. Does an exponential operation like this grow faster or slower than squaring? Much faster. X squared looks like this. But let's look at y equals 2 to the x. And I'm going to kind of get this down. This is why I have graph paper on this. Y equals 2 to the x is what we call an exponential function. Something that if you spent some time on that 10.0 thing, you would have seen that on the first page. Lots of examples of exponential functions. An exponential function happens when your exponent is the variable. And this is the first sort of semi-new operation, but it's not the major point of today. And yet to build the major point of today, I have to spend some time on exponential functions by doing the single greatest way you have to graph anything you've ever not graphed before, the t-chart. This is why I asked you guys to do a t-chart on those graphs. And we're going to do this with several numbers. I'm going to plug in -3, -2, -1, 0, 1, 2, and 3. I'm going to do only those because anything outside of that, I'm not going to be able to see the y values on something that I graph. I'm really stretching it as it is. So while I start putting the grid down, you guys are going to be putting in the t-chart values. Go. Plug in the t-chart values. X is -3. What is 2 to the x? What's 2 to the -3rd? Let's continue the pattern. 1/8. 1, 2. So not only as we move to the right does an exponential graph start getting large very quickly. There's 1/8-ish. There's 1/4, somewhat-ish. There's 1/2, 0, 1, 1, 2, 2, 4, and then 8. But it's a graph that looks like it's not a great connection of the dots. And I'll try to do this in a different color, actually. It's actually not terrible. It's a graph that, as x gets big, y gets uber big. Y gets ridiculously large. If I wanted to go out 100 places, I'd have to do 2 to the 100th power. That is a ridiculously large number. And you can't scale these things well. Let's say I zoom out and try to graph the next point, 416. I already can't graph the next point, 532. And every time I zoom out, I just get one more point, and that's about it. And I keep shrinking these things down to the point where I can't graph them. What we're going to do is focus on a different operation. This is an exponential growth curve, but I want to focus on the operation that actually takes these and, watch my fingers, switches them. An operation that inputs 1/8 and outputs -3. That inputs 1/4 and outputs -2. That inputs 1/2 and outputs -1. That inputs 1 and outputs 0. That inputs 2 and outputs 1. 4 becomes 2 and 8 becomes 3. What do you think 16 becomes? So the operation, if this is x, this is called the log or logarithm base 2 of x. That's exactly how I want you to say it. Not log 2x, log base 2 of x. The base indicates how are we building the exponent. I'm trying to convert 1/8 into an exponent, but I need to know of what base. And this is of base 2. The graph of this, 1/8 -3, 1/4 -2, 1/2 1, or -1, 1, 0, 2, 1, 4, 2, and 8, 3. The graph is a graph that looks like this. This is the log base 2 of x, and this is 2 to the x. Don't be confused. The graphs do not go on the same graph. I'm graphing on the same graph so you can see the comparison of the two. I'm even going to put a little separator so you can see that these are different graphs. And it's not a coincidence that I'm using this as a separator, which happens to be a line of symmetry that perfectly reflects the two of these graphs. This concept is 10-3. We're not going to do it this year. It's on inverse functions and their graphs. We'll do it in pre-calc. But this is what happens when every xy point becomes a yx point. You reflect about y equals x. The graphs have different concavities. That's a calculus concept, but I want you to see what I mean by that. This graph here, its concavity is such that as the graph increases, the amount that it's increasing is also increasing. It's getting faster more. This graph is what we call concave down. Even though it's an increasing graph, it's decreasing the amount it's increasing. it's slowing down how much it's increasing by, but it is still an increasing graph. It will never stop being an increasing graph, but certainly you can see it's not increasing the same way the other one is. Those are what we call different concavities, and that's, again, a calculus thing. But back to this. I want to talk about this little thing here, a logarithm. And this is going to take many, 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 many exposures to start to get this. So I'm not expecting this to happen right away. We're going to work our best with this. A logarithm. A logarithm inputs a number and a base. So you have actually two inputs that are going on here. You should be used to that. You've had two inputs with addition. You've had two inputs with multiplication. This is two inputs. It inputs a number and a base, and it outputs the exponent that relates them. It inputs a number and a base, and it outputs the exponent that relates them. So for instance, the log base 3 of x means you can plug in an x and out comes an exponent. And initially, I want you to think about this as taking a number and shrinking it down. I'm going to plug in a super large number and I'm going to shrink it down. I'm going to do that by saying, what exponent is this? So let's say I did the log base 3 of 81. Not a super huge number. But the log base 3 of 81 is the exponent that relates 3 and 81. 3 to what power is 81? 4. This number right here, this is a number. That is equal to the number 4. They are both the same thing. That is tricky too. I know that many times you guys were young and you saw this. 3 times 4. And it would mean, do me. Do something. Do that. Do that thing. That's now on YouTube. Okay. What is 3 times 4? But have you ever encountered something where you wanted to write 12 as 3 times 4, to go backwards? Maybe when you cancel and you want to divide something out. You want to express 12 as 3 times 4. Maybe when you have 12x plus 3 and you want to express 12 as 3 times 4 so you can factor a 3 out. You guys have become a little bit more comfortable in Algebra 2 doing substitution the reverse way, taking something that seems to be more complicated and actually writing it that way. I want you to see this as a substitution, not as a simplification. 4 is the same as log base 3 of 81, and 81 is the same as, or log base 3 of 81 is 4. And in fact, we're going to actually work a little bit in writing them. If I write an equation, the log base 3 of 81 is 4. And this is called logarithmic form because it's a form that relates the numbers. Can I write those 3 numbers in a different way that relates them in the same way? 3 raised to the 4th power is 81. This is shuffling the numbers in a different way, much like you might have done when you said 2 times 3 is 6, and 3 is equal to 6 over 2. Doesn't that really tell you the same relationship? This is the same idea. This form right here is called exponential form. You will be interconverting between the two of these forms quite frequently, especially in the early parts of this chapter. And then even next chapter, you will convert between the two of them. The log base b of x equals y means b to the y power is equal to x. So sometimes a log can be really simple about what it means. It can be really, really, really simple. Let's take a number that's crazy, crazy, crazy large. Yeah, that's actually the number of different possible 5-minute audio tracks that you could make on a CD.
And our question, why were you writing that out?
We were talking about super large numbers. Let me ask you a question about that number. Well, I have this really, first of all, you realize that that is a stupidly large number. And by stupidly large, that number is actually more than the number of protons there are in the universe. By large scales, that's more than the number of protons that there are in the universe. But what would be the first thing that you would want to know about that number? The very first thing. Just give me a hand. Give me one hand. I want you guys to no, stop shouting. I want an intelligent response to this. What would be one of the first things you may want to know about this number? Okay. Now, before what it represents, what do you want to know about this? What's like one of the things that you might track? Carson.
How many numbers are in that?
How many numbers are in there? So you basically want to know how many numbers are here. How relevant do you think this 8 is?
Not at all.
I'm going to tell you that 6 is also not that relevant when you're talking about a number this large. What is more relevant is how many digits follow. So I'm going to look at that and try to guesstimate, because I don't want to spend a lot of time counting. And we're going to guesstimate that this is about probably 65, 70 digits. Let's say that this is 70. Let's say that this is the number 10 to the 70th. And I'm going to do the log base 10 of that number to shrink it down. I want to do the log base 10 of 10 to the 70th. And before you worry and think this is a crazy operation, what this is asking is, what exponent changes 10 into 10 to the 70th? What exponent would you have to raise 10 to get to 10 to the 70th? Do you see how that's kind of a cyclical question here? I'm literally asking you 10 to what power is 10 to the 70th? That is 70. This is 70. If I do a log base 10 on that number, it's going to tell me how large that number is. It will output the number of zeros with a little decimal that follows. I mean, it's going to be 70 point something because it's not, as an exponent of 6. Yes, Krishna?
How did you get the 10 from that number?
Well, I know that 10 to the 70th is a 1 followed by 70 zeros. That's what 10 to the 70th means. 10 times 10 times 10 times 10. And every time you multiply by another 10, you add another 0. I guesstimated there's 70 digits in there, and I rounded it up. I don't want to do the log base 10 of that number just yet. We got to learn basics about what a log is before we get to the crazy things. Yes, Aiden?
So on that number, that's how many what?
Later.
Did you take
Later.
the time to
Later.
write that out?
Nope.
I'm so confused what it is.
Okay. So here's a question that is on something we've done before. Yes, Jania? Because if I took 10 to the 7th power, that would not be the same as 10 to the 70th power. I need to figure out 10 to what power is equal to 10 to the 70th. What? No, you're not seeing this. 10 raised to what power equals 10 to the 70th? What would have to go in that box if they're the same thing? 70. That's what I'm asking. So we're going to do the same thing here. 5 raised to what power is equal to the 5th root of 1 6/25. Do you guys see how this builds on what we've been doing?
Yeah.
Don't work your way forwards. Take the time to rewrite this right side as a power of 5. Just take a minute and let's bring it down step by step. 6/25 is 5 to the 4th. You should know that. You should know 5, 25, 125, 625, 3125. Next, we're going to make 1 over 5 to the 4th be 5 to the negative 4. And then 5 to the negative 4/5. So let's carry this down again. 5 to what power is 5 to the negative 4/5? Negative 4/5. So this whole thing up here, that equals negative 4/5. And that was one way you can do it. And I like that way because it uses what we did before. I always love it when we've done what we did before to solve a new problem. Now, logarithms can work for smaller numbers too. So you guys know that when we measure things in science, we always use metric, both for big and for tiny. And when we're talking tiny, any of you who go to a biology field, we do it in terms of every threes. Every 3 decimal places becomes a new prefix. So no one ever uses the prefixes for every single bit of the way. You use milli for thousandth. You use micro for 1,000 thousandths, 10 to the negative 6. You use nano for 10 to the negative 9, and you use pico for 10 to the negative 12. Those are the standard prefixes you tend to use for small amounts. I want to do a log base 10. I'm doing base 10 because I'm counting by 10s both ways, forward and backwards. A log base 10 of 1 times 10 to the negative 12th, which is a picometer or a pico something. So, well, first of all, 1 times anything is itself. So that's really the log base 10 of 10 to the negative 12. What would that be? Negative 12. So by doing the log base 10 of the number, I bring back what exponent it is. A log inputs a number and it outputs an exponent. Number 4. Because I wanted to keep this up for people writing on that. Solve the log base 3 of x equals negative 3. A strategy you will have when you have an equality like this is to change the form. Go back up just a little bit to where we did the logarithmic form versus the exponential form, and just rewrite the numbers. Base, what's the base? Raised to the exponent, a logarithm is equal to an exponent, equals x. And suddenly you have one of the world's simplest problems. 3 to the negative 3 is x. X is... Yeah. I created this problem here. So I'm asked you to solve that. Now, I don't want you doing this, but you can see it in your head this way. I really don't like shortcuts, but a lot of people like writing 3 to the negative 3 as x, and the log base 3 of x is negative 3. Just it helps keep things in mind about where it is. I want you thinking, though, base raised to exponent equals argument. And if I write the log with a base here, this is called the argument, equals the exponent. We can all use the same words here. Log with a base as a subscript of an argument equals the exponent means that a base raised to an argument, or raised to an exponent, sorry, equals an argument. An argument's a general word for anything you're doing an operation of.
Why do you call it an argument?
It's a word that means something you plug into a function. It's a programming term too. Okay, Jania. Okay, back up, guys. Please don't talk while someone else is talking. Yeah. I'm changing the form. I'm taking this logarithmic form right here. And let me copy down something that we wrote up above here. We wrote this from up above. We wrote that the log base b of x equals y means that b to the y power is equal to x. So I took this and I wrote it in that second form. I've shuffled the numbers around. This is a lot of what you guys are going to have to practice doing. You will shuffle back between log form and exponential form a lot. Yes, Hannah?
What if the question is log 3, or log base 3, y equals negative 3?
Log base 3 of y equals negative 3? Well, you just say y equals 1/27. You only replaced x and y. These x's and y's, when I wrote that rule, aren't set as x's and y's. I just put them there as whatevers. Okay, let's go move on to some other ones. Log base x of 8 equals 1. I want you to tell me what base would make that true. Remember, you can rewrite this in exponential form. Shall we animate this? If you watch this animation, it might stick in your heads. When I shuffle the numbers around, what I do is this. Uh-oh. So what is x? Goodbye, log. X to the first power is equal to 8. X would be 8. Let's simplify this one. Log base 7 of 7. 1. I want to show you a strategy for this one if you're really kind of confused a little bit. What I can do is I can say that this is equal to x. I know there's no x here, but I'm going to say it's equal to x. So that I can shuffle this around and rewrite it again. 7 to the x power is equal to 7. That gives you a lot better idea of what x is going to be. And that's 1. Log base 2 of the cubed root of 1/4. Remember that strategy I just did about 0.67 seconds? Well, actually, a little bit more than that. I would try that here. I'd say equals x. And we're going to write 2 to the x power. I'm realizing I can play with colors here to try to help this a little bit. So this was log form at the top. I moved it to exponential form. The reason I did that is because now I have created a problem that looks like other problems we've done. It's a great critical thinking skill, is to take a problem you've done before and make it or haven't done before and make it a problem you have done before. So I have 2 to the x. Equals, let's convert this now to a base of 2. 1 over 2 squared. Cubed root of 2 to the negative 1, or negative 2, sorry. And this would be 2 to the negative 2/3. Which means that, what is x? Yeah. And I'm going to change all these x's to green so my process can match. Okay. Nope, I'm going to give you one to do on your lonesome, and I'm going to pause it so Ben can do those on his. Okay, log base 1/9 of the 5th root of 1 over 729. Okay, something I'm not YouTube recording. Okay, yeah, for all of you guys that did x, I would do that here. So you go 1/9 raised to the x power is equal to the 5th root of 1 over 729. I like making these things easy, which means I'm going to bring both sides down to 3. Left side, 1/9 is 3 to the negative 2. Right side, I have the 5th root. If you didn't know 729 was 3 to the 6, factor it. You should suspect that it's a power of 3 because the left side's a power of 3. So just take 81, which you know is 3 to the 4th, multiply it by 3, and multiply it by 3 again. So this would be 3 to the negative 6. Let's keep bringing this down. 3 to the negative 2x is equal to 3 to the negative 6/5, which means that negative 2x is equal to negative 6/5. And if I divide the left side and the right side by 2, or negative 2, I get positive 3/5. So that's what this whole thing simplifies to. Okay, we're going to close today with a couple of rules. Aw, sad. Poor Maddie. Okay, log base 2 of 2. What does that simplify to? 1. Log base 11 of 11. Give me a rule. Log base. Yep. So we do log base b of b is 1. This is how we kind of come up with a few of these rules. Now let's do 3 more, 2 of which will be the same idea, and the final of which will be the rule. Log base 2 of 1. Careful, 2 squared is 4. 2 to the 1/2 is the square root of 2. 2 to the 1 is 2. 2 to the 0 is 1. Remember, you're asking me I'm asking you what the exponent is. 2 raised to what power is 1? Log base 11 of 1.
0.
Log base b of 1.
0.
Log base 2 of 2 to the x. 2 raised to what power gives you 2 to the x? Log base 11 of 11 to the x. Now let's get a rule down. Log base b of b to the x. Finally, log base 2 of 0. 2 to what power gives me 0? Undefined, doesn't exist. Log base 11 of 0. Log base b of 0. Undefined. It is impossible to take a base, raise it to a power, and make it 0. Bases themselves must be positive. We're going to work with that a lot on domain. Bases must be positive, and bases cannot be 0. We have a little bit. No, we don't. I won't make you guys go over homework right now, but let me write this down. Tomorrow, I need you to come prepared. We're going to talk about the last couple assignments. Please see me, though, if you have questions on this before class. It's very, very, very helpful to get that dialogue out. Good luck, and I wholly expect that for tomorrow's homework, you guys have quadratic substitutions